What's going on, everybody? This is Mr. Diamond, and we're going to work out our first example for inelastic collisions. Now, this one is more of a proof of concept kind of problem. It's not even going to really be that difficult, but it's going to prove to you why kinetic energy is not conserved when you have an inelastic collision or an inelastic collision. So the example we had looked at previously was you have a 1,000 kilogram train car. I think it was actually 10,000. 1,000 kilograms is not actually that big for a train car. So you have a 10,000 kilogram train car, and if it wasn't what I had the last time, well, it is now. Now it's a 10,000 kilogram train car. 10,000 kilogram train car is driving down the track, and it's going to be moving at 24.0 meters per second. There's no friction, there's no anything like that that's going to be affecting it, and then it's going to collide with a 10,000 kilogram train car, an identical looking one. They're going to lock together, and they're going to continue traveling forward. Now, we could do some solving here. We could use that momentum 1 is equal to momentum 2, and we could solve out with that. But I talked about how this one, at least conceptually, you can kind of wrap your head around why it's going to be the way it is because of the fact that these are identical masses. If this is identical masses, if momentum has to stay the same, and if momentum is equal to mass times velocity, we are doubling the mass when this attaches to it. Momentum has to stay the same. If we double the mass, the only way momentum can stay the same is if we cut the velocity in half. So we said V2 must be half of 24, which is 12 meters per second. And if you actually go to solve it, you would end up with the momentum at stage 1 is 1,000 times 24 plus 0 times 1,000, because this doesn't have any momentum, so that cancels out. This side here, you would have 2,000, because that's the mass, times V2. Solving for V2 would give you 1,000 times 24 over 2,000. And then we could simplify that 1,000 to 2,000 into 1/2 times 24. And it would get us to the same place. So I know I rushed through that, but we already did this in class. We already talked about this. So we're going to start from just the point of, we know that V2 is 12 meters per second. So the question that we're asking here now is, how much did KE change? I think the way it's worded on the worksheet is how much did you lose, but let's go in assuming we don't know that we're actually going to lose kinetic energy. We aren't 100% sure that this process. We said there's no friction. We said that it's going to collide. They're going to lock together. So, and momentum is even being conserved. So maybe kinetic energy is going to stay the same. So let's check it out. Well, in example 1, or in our first part, I also forgot these are 10,000s. It's going to make me have to do my math correctly later part. So let's look at the KE that we have at position 1. So first we have a 10,000, our one that's at rest. We're going to ignore that. We're not going to worry about this one that was still. That's not contributing to the kinetic energy. So you have 1/2 mv squared. So we're going to have 1/2. Mass is 10,000. And then our v in this case is 24 squared. Plug that in. So I'm going to do 5,000 times 24 squared. We get the very large number, which makes sense because we're talking about a train here. 2,880,000 joules of energy. So that's a lot of joules. But then let's check what KE2 is. So KE2 is going to be equal to still 1/2 mv squared. And we know momentum was conserved. That's why we were able to do this problem. We're going to do 1/2. Mass is now 2,000. And velocity is now 12. We're going to have that squared. So it seems like it's, 20,000, not 2,000. We're going to have a very different answer if we do that. Also, I did type in 5,000. That was correct. Okay, so now we're going to go ahead and plug in. We're going to do half of 20,000, which is 10,000, times 12 squared. And this time we get 1,440,000 joules. So notice that by doubling our mass, cutting our speed in half, we actually cut our kinetic energy in half. Not only did it change, not only did we lose it, even though there was no friction, even though there was no other impact, there was no heat exchanged whenever it collided with it, even though all of the actual collision part of it, even though it just locked in place smoothly and then continued traveling forward, we still lost a whole bunch of kinetic energy. Now, I mentioned there's like no friction and stuff like that, so where did this kinetic energy go? In reality, it actually would have been lost due to probably all of that heat and all of the friction and all of the impact and stuff like that, and making sound, and like there would have been a bunch of places that would have been lost. But because these collided together and had all of the stuff happen, not on the tracks, but when they collided, that's where we're going to lose all of that energy. All of that energy is going to be used up in all of those types of exchanges. And if you kind of think about it as the fact that like this was stationary, remember this also has inertia. It's going to not want to move. Remember, inertia everything has, even if it's at rest, whereas the first thing didn't have momentum. So some of that energy, of that kinetic energy, had to be used to get that 10,000 kilograms to start moving, to even begin to move. So we lost a whole lot in that process. That's probably where most of this went. I'm sure some of you were like, it doesn't make sense, we would have lost 1,000,000 joules to heat, like wouldn't it have spontaneously combusted? Well, no, it was because we had to overcome the inertia of that object that was sitting at rest. That's where most of it was. But we would still probably lose a little bit to it, to friction and heat and stuff like that. But that's going to be negligible. Most of it is going to be just from getting the cart to move. All right, so how much did we lose? We lost 50% of the KE was lost. All right, if you have any questions about this, please shoot me an email. Like I said, this is more of a conceptual proving question. Usually your inelastic collisions will be either something like this, or they'll have things involving like impulse, or they'll have something involving the momentum that you're given. There'll be a little bit more going on, kind of like how this one started with doing a momentum problem and then solving for KE and PE. These are also more likely to involve KE and PE when you're solving the problems, but the next example will show that in a little bit more detail. In the meantime, though, this has been Mr. Diamond. Like I said, if you have any questions, please shoot me an email. Otherwise, have a good rest of your day, everybody.